Okay, so in this video, we'll talk about a characterization of trees. And what this means is basically we're giving conditions that are both necessary and sufficient for a graph to be a tree. So let's start off by telling you what this characterization is. If you have a connected symbol graph, okay, so just assume that we have a graph that's connected, right? Otherwise can't be a tree, and it's simple as well. Then the graphs that are trees are exactly graphs that satisfy this equation. The number of its edges is equal to the number of its vertices minus 1. Okay, why is that true? Well, that's what we're proving here. And you can start exploring yourself. If you just start drawing any tree, count the number of vertices, count the number of edges, right? So here you have 6 vertices and you have 1, 2, 3, 4, 5 edges. 6 minus 1 is 5. Okay, so how about a path? So it's clearly true for any path. If you have n vertices in a path, then you'll have n minus 1 edges. How about something that looks like this? That's a tree, right? It doesn't have any cycles. Same thing. This has 8 vertices and 7 edges. So this is always going to hold for any tree. And in fact, the converse also holds. If I say that I have a graph that satisfies v minus 1 equals e, then it's a tree. Okay, so how would we prove this? Well, it's 2 directions, right? You want to show that if it's a tree, then you have that equation. Also the other way. If that equation holds, then G is a tree. So let's prove it one way first, which is, given that you have a tree, why is it true that the number of edges is 1 less than the number of vertices? Okay, so we're going to do this by induction on the number of vertices in your tree. Right? And so this is our predicate here. P of n is the statement all trees with n vertices have n minus 1 edges. Okay, so you can do it for, let's check a number of base cases here. N equals 1. Okay, well, it has no edges, right? Because it's simple, so it can't have loops. So it's true. N equals 2. Just want to check, just for sanity, right? If you have a tree with 2 vertices, well, it has to be this one, right? Because the tree has to be connected. So E equals 1, right? The cardinality of E equals 1. So let's proceed now with the induction step. And in this case, we're going to assume that P of k minus 1 is true. Right, so this statement holds, which means any tree with k minus 1 vertices has k minus 2 edges. And we want to show P of k is true. And, well, how would we do that? So we want to show here that any tree with k vertices has k minus 1 edges. So let's take an arbitrary tree on k vertices. So suppose G is a tree with number of vertices equal to k, yeah, to just k. So now what we want to show is that it has k minus 1 edges. Okay, so how are we going to use the induction hypothesis here? The induction hypothesis tells us something about all trees with k minus 1 vertices. Right now we have a tree, right? We have a single tree G with exactly k. So maybe we can remove a vertex from G and get something smaller with just k minus 1, on which we can apply the induction hypothesis. Okay, so how is that going to work? Well, remember that we've proven that G has at least 2 leaves. Right, because it's a tree. So let's say small v have degree 1. Okay, so what that means is you have your graph G, it's a tree, you have V, which is a leaf, and it's connected to like some other stuff here. Okay, so let's remove let's remove V from our tree. So consider the graph. Let's remove small v from the vertex set. And E, I don't want to give a name to this edge, so I'm just going to say, consider the graph obtained by removing V and the edge incident to it. Well, I can give a name to this graph. I can say the graph is G prime. Then G prime is a tree on k minus 1 vertices, right? We started with a tree, you remove V and one edge, and what you're left with is now something that still has no cycles, right? If it did have a cycle, then the original graph couldn't have been a tree, and that's still connected. And so what do we know about G prime? By the induction hypothesis, the number of edges in G prime is equal to the number of vertices on G prime minus 1. I'm just going to say k minus 2. Well then, aren't we done here? Therefore, the number of edges in G is k minus 1, right? Just add that edge back that you removed, right? From G to G prime, we removed one edge. Since G prime has k minus 2, G must have k minus 1. Okay, so that proves this direction. We've shown that if you have any tree, it has exactly v minus 1 edges, right? Or if you say it has n vertices, then it has n minus 1 edges. How about the reverse? If you start with a connected simple graph that has number of edges equal to the number of vertices minus 1, show that G is a tree, which means, well, you already know G is connected, right? So really what this means is We want to show G has no cycles. I'll pause the video right now, or I'll let you pause the video right now and think about this for a minute. So pause the video right now. Okay, so what did you come up with? Were you able to prove this fact? So let's see. What are some things we can do here? So let's say let's try to do it by contradiction. That G has a cycle. Right? We want to prove G has no cycles, so let's assume that it has one, or at least one. So what I'm going to do is I'm going to remove an edge from that cycle. Okay. So okay, let's give a name to this cycle. Or no, we don't need to remove an edge from this cycle. To obtain a new graph, G prime. Right, so pick an edge on the cycle, remove it. Now what can we say about G prime? Well, for sure, G prime is still connected, right? If your original graph had a cycle, something like that, in your graph G, so vertices possibly connecting somewhere else, and you choose one edge in this cycle and remove it. Well, between any two vertices in this new graph, you're still going to be able to connect them because the original graph was connected. Okay, so one way you could argue that properly, right, or more convincingly, if you will, is to just say the following. Since any pair UV of vertices in G or in G prime, they have the same vertex set, will still have some path between them. And the reason for that is because, well, in the original graph G, you could have connected them. But if your UV path in the original graph G used that edge that you deleted, well, it was part of a cycle. That means you could have just went the other way in the same cycle and still obtained a UV path that didn't use that edge. Right? And that's the reason why G prime is connected. And so let's keep going, right? G prime remains connected here. So what if it still had other cycles? We can just keep going, removing one edge from every cycle that we see until we get a graph with no cycles. Okay, so keep removing edges from cycles until we get some graph, I don't know, like H maybe, that has no cycles. What do we know about H? H is connected, and it has no cycles. Well, apparently, H is a tree now, right? So we started with G. Since it had the cycle, we were able to keep removing edges from G and destroy all those cycles, so that we end up with H, which is connected and has no cycles. So H is a tree. But how many edges does H have? Okay, this is where this comes in. The number of edges of G is the number of vertices minus 1. But the number of edges in H, since we removed at least one edge, right? There was at least one cycle in G, is strictly smaller than the number of edges in G. Well, H and G have the same vertex set, right? Nothing changed with the vertices, we were just removing edges. So this is equal to Vg minus 1, which is the same thing as Vh minus 1. And this is our contradiction. What does it contradict? Well, it contradicts the previous result that we just proved. Because if H is a tree, then H should satisfy that equation. Edges in H should be equal to vertices of H minus 1. But here we have this inequality, which shows that it's not. Therefore, in other words, G must have had no cycles to begin with. And that's the end of the proof. And now we have both directions. That gives us our characterization of trees. Okay, so just to summarize, I guess. G is a tree if and only if number of edges is equal to the number of vertices minus 1.